The universe is not static. It evolves all the time and grows in all directions. It's expanding, and scientists found this out almost a century ago. And it's not at a stable rate. The more time goes by, the faster the universe expands. As this happens, stars, planets, and galaxies move farther and farther apart, which leaves more space between them. If that's the case, the universe is supposed to become colder as it expands, right? After all, it was a lot denser when the Big Bang happened, and a lot hotter. As it was expanding, space was cooling down, which created conditions for planets, stars, and other space objects to form. Yeah, that's not exactly the case now. Scientists were surprised to hear it too. But our universe is actually getting hotter. They observed the temperature of cosmic gas farther away from our home planet compared to young gases closer to the Earth. Since we measure distance in space by light years, farther areas are like going back to the past, and regions closer to us are like observing the present day. They found out the temperature of a gas in space has gone up more than 10 times in the last 10 billion years. Now, the temperature of the cosmic gas that's spread all across the universe can get to around 4 million degrees Fahrenheit. Wow! As the universe expands, gravitational force does its part and pulls gas and dark matter together. It's doing some pretty hard work there. It creates galaxies and clusters of galaxies out of them. And this process is totally chaotic. It's so messy that more and more gas heats up as all of this is happening. Space was extremely hot when it was just forming 13.7 billion years ago. What if it gets warm like that once again? Scientists are observing the situation. They found out the temperature in space increased by measuring cosmic gases using something called redshift. They generally use this method when they want to see how far away some space objects are. Those that are closer to us have shorter light wavelengths. The farther some object is, the longer its light wavelengths are. And they can now determine the temperature of a certain object from its light. On average, space is a pretty cold place. The glow that's left from the Big Bang is called the CMB, which is short for the cosmic microwave background. It's so powerful and intense, it bathes the entire universe in light. It's the only thing that significantly heats up matter. But there are many smaller mechanisms that help to heat up matter in the universe, and they could go crazy if space warms up. Like stars. They emit radiation that affects nearby dust and gas. They radiate throughout the far infrared too. When a star is at its early stage, the radiation coming from it forms protoplanetary structures that look like disks. They primarily form in a single plane, and a bright central star produces spectacularly illuminated gas, and there are blue reflections of this gas. It was like that with our planetary system too. Strong energy and gravitational forces cause collisions, dust, and gas in an uncontrolled vortex that's forming planets. That's why most planets in our solar system orbit in the same direction. That's the direction this giant whirlpool was spinning a long time ago too. Active stars, colliding galaxies, stellar cataclysms, black holes, neutron stars. The universe has so many sources of energy. And when you surround normal matter in space with such an energetic environment, it heats up drastically. When you heat something up, it radiates that energy away in a certain way. In most cases, galaxies have just a couple of areas where stars are forming, at regions where gas is collapsing. A bubble that surrounds that area contains ionized hydrogen. 3/4 of our sun is hydrogen. Thanks to that hydrogen, the sun keeps us warm. In its core, hydrogen transforms into helium and causes atomic fusion. Yep, that's how our sun releases its energy. Radiation heats all that gas to thousands and thousands of degrees. At the same time, it ionizes a large number of atoms and molecules, which basically means it turns them into ions. Atoms are neutral particles, and ions are either negatively or positively charged particles. If the universe heats up, our sun might too. If its temperature hits 30,000 degrees Kelvin, it could become hot enough to ionize all those materials it had previously ejected, and it could create a real planetary nebula. This would be a nebula in the shape of a ring that forms because of an expanding gas that surrounds an aging star. As the temperature goes up all the time, hydrogen ionizes. At a few thousand degrees, this could turn the nebulae in our solar system pink with emission lines. Our sun could come to its end if it reaches the temperature of 50,000 degrees Kelvin. If you could float in space and come closer, you'd see it glow in eerie green tones because of doubly ionized oxygen. Higher energy phenomena make more galaxies collide. This heats gas even more and eventually results in X-ray emissions. What about black holes and radiating neutron stars? When they go crazy, they can shape whole galaxies, and who knows what more. Maybe we'd have more masers too. Those are natural lasers our universe produces. They arise when big populations of molecules receive large amounts of energy. By now, scientists have found the strongest, yet the most distant maser. So powerful, it's more luminous than the light 6,000 suns would produce, and in just one emission line. Maybe then we'd discover even stronger masers. That's in the case that we're even going to be here at all. Because as the universe is getting hotter, cosmic radiation is getting stronger. Not so good for life on Earth. Increased cosmic radiation could harm us. Who knows if life would even be possible on Earth in that case, or if the powerful gravitational force would pull our home planet too, and crash it into another one. But maybe life as we know it wouldn't completely disappear. Or, if that happened, it could possibly somehow find its way once again, maybe in the distant future. There's a possibility our universe could support life at its early stages. Doesn't look like that when you think of the chaos the Big Bang caused, right? But that was only in its mere beginnings. After things had settled down a bit, the dregs of enormous, earliest stars formed rocky planets. In our solar system, those are Earth, Mars, Mercury, and Venus. You can't set your foot on the rest of them since they're gas giants. Back in that time, radiation was quite intense, so rocky planets had an adequate environment to form, since it takes a lot of energy to whirlpool dust and particles and bake a planet in the end. This period of time coincides roughly with that when the first stars formed in our universe. Ancient stars were way bigger than our sun. They lived shorter though. They would have just exploded as supernovas on their end, and they would leave heavy metals across the space around them. Those are the particles rocky planets formed from. Radiation spread around the whole universe back then. It has changed over time. Today, it's almost an absolute zero. 400,000 years after the Big Bang, when hydrogen atoms were forming, CMB was almost as hot as the surface of our sun. And about 15 million years after the Big Bang, its temperature was close to room temperature, which is around 80 degrees Fahrenheit. These things were happening across the universe, so there were many planets that could potentially hold life. If we were one of those ancient worlds, we wouldn't need a star to keep us warm. CMB would be enough to do it. So, it's possible that life in space is way older than we think it is. There could have been ancient worlds with liquid water on their surface. What if there were some primitive forms of organisms, like on our home planet a long time ago? Or even more developed ones? Perhaps we'll find out one day.
That's it for today. So hey, if you pacified your curiosity, then give the video a like and share it with your friends. Or if you want more, just click on these videos and stay on the bright side. Now, as a child, weren't you taught not to play with your food? Well, apparently these astronauts weren't. Floating Jell-O cubes across the cabin while in zero-G is a lot of fun. But it is also a sign of a potential problem called space euphoria. No one ever considered that extreme happiness in space could become a severe problem. But it can become a serious problem, and that's no kidding. For many years, space euphoria went undetected, although it was right there, front and center for all to see. When Apollo 14 astronaut Alan Shepard smuggled golf balls onto the moon and tried to create a tiny moon for the moon by attempting to hit a golf ball into orbit around the moon, everyone thought it was funny. Apollo 16 astronaut Charles Duke thought it would be funny if he tried to compete with the 1972 Olympic athletes back on Earth. He attempted to outjump the Olympic athletes to benefit from the 1/6 gravity on the moon. Duke jumped so high that he rotated onto his back and fell crashing onto the life support system in his backpack. It could have been a fatal fall if the bag had cracked. Duke's commander, John Young, said, "That's not funny," and it sure wasn't. Yet, when Apollo 17 astronauts began dancing and singing children's nursery songs while collecting rock samples, everyone still thought it was cute. Space euphoria again went unnoticed. As early as 1965, when Ed White became the first American to walk in space on a tethered spacewalk, his space euphoria became evident. He stayed out much longer than was necessary to test his mobility with the very first jetpack, or MMU as it was called, officially the Manned Maneuvering Unit. In his own words, "I'm not coming back. This is fun." Finally, when ordered to return to his Gemini spacecraft, Ed White said it was the saddest day of my life. Obviously, something sinister is at work with space euphoria. Weightlessness, combined with the view of Earth passing below, creates an exhilaration that overcomes all sense of duty. It is the great danger of space euphoria. Now, in hindsight, the effects of space euphoria could be seen when Apollo 17 astronauts drove the lunar rover on the moon. They exceeded the recommended speed limit and could be heard whooping and yelling as the rover rocked onto two wheels, even becoming airborne at times. Canadian astronaut Chris Hadfield was busy at work during his tethered EVA, extravehicular activity, when he paused to look over his shoulder. The glory of space smacked him in the face. He was so emotionally overwhelmed at the magnificent beauty of the Milky Way galaxy that tears began to fill up Hadfield's eyes. Now in space, tears do not flow down your cheeks. They pool up in your eyes. Hadfield had become blinded by tears of joy. But Hadfield, against protocol, refused to tell his supervisors on Earth. Only after he was no longer able to work did Hadfield speak a famous quote, "Houston, I have a problem." It was a direct result of space euphoria. Astronaut Hadfield managed to get back into the space shuttle, but his EVA was not fulfilled. Space euphoria had interfered. There is another aspect of space euphoria that deserves serious attention. It is something called the overview effect. Weightlessness in space affects everything from the physical and psychological health of the astronauts to the physics of using all the mechanical equipment of the spacecraft. However, weightlessness in space is not due to a lack of gravity. Astronauts orbit Earth less than 300 miles up, called LEO, low Earth orbit. There's plenty of gravity in low Earth orbit. The Earth's gravity keeps the Moon in orbit, and the Moon is about 250,000 miles away. In fact, a 150-pound astronaut would weigh 142 pounds in LEO. Weightlessness in space is due to free fall, not lack of gravity. What goes up must come down. The rocket blasts off, and about 8 minutes later, the engine shut off. The spacecraft begins to fall back to Earth. Fortunately, by this time, the rocket has achieved orbital velocity, which is about 17,500 miles per hour. So that it falls towards Earth but never hits the Earth. It keeps falling and falling around and around, precisely in the same curved path as the surface of the Earth. It's in orbit. It is free fall. Even though everyone calls it zero-G, it's not. If you were to place a bathroom scale under your feet when in free fall, it would show 0. You would weigh nothing. That's because the bathroom scale is falling too. The exciting thing is that astronauts retain all their muscle power. Their mass stays the same. Therefore, they can lift heavy equipment in space that would weigh hundreds or even thousands of pounds on Earth. Astronauts become superhumans in space, and that creates another unusual situation. There are lots of unusual situations in space. On the very first trip to the Moon, the Apollo 8 astronauts were not even scheduled to look back and photograph the Earth. Apollo 8 astronauts took only a limited number of pictures of Earth. That's unusual and kind of weird. But Earthrise from the Moon became perhaps the most influential environmentalist picture of the 20th century, and it wasn't even planned. But this is the key to understanding the overview effect: surprise at the unexpected. Even today, almost all globes of Earth are not of Earth. Globes in schools and libraries show each country, usually in different colors. Each country, sure enough, contains a star, but it is to mark the capital city of that country. It is not how the Earth looks from space. These globes are not globes of the planet Earth. In fact, it isn't easy to even find a globe of the planet Earth. Read the labels on these classroom globes. The geopolitical world. These are globes of a place called the world. There is no planet called the world. The world does not live in space. It lives on someone's desk or shelf. The definition of space is geological in origin. Space is defined as existing up to, but not including, the atmosphere of Earth. Earth isn't even an astronomical object. It explains why the very first mission to the Moon, the Apollo 8 mission, had not scheduled any pictures of Earth. Selfies weren't invented then. It also explains why the psychological impact of seeing Earthrise from the Moon was so profound. It was a unique and totally new perception for which any and all humans were utterly unprepared. Seeing Earth in space was a complete surprise. Imagine yourself floating in space outside the spacecraft. You are surrounded by the Milky Way galaxy blazing with millions of stars. The planet Earth is a blue marble passing beneath your feet. Pretty heady stuff. How would you react? Would it change you? Apollo 9 astronaut Rusty Schweickart felt strongly that he was what he called the sensing element for humanity. What does he mean? It's the overview effect kicking in. Schweickart felt that he was connected to all the people on Earth. He compared it to being born into a new existence. And astronaut Schweickart is not the only one who felt the overview effect. Apollo 14 astronaut Edgar Mitchell had this to say about being in space. It was rather an extension of the same universal process that evolved our molecules, and what I felt was an extraordinary personal connectedness with it. I experienced what has been described as an ecstasy of unity. I not only saw the connectedness, I felt it and experienced it sentientally. I was overwhelmed with the sensation of physically and mentally extending out into the cosmos. Some years after returning from space, astronaut Mitchell started an institute to study the brainwaves of people who had been in space. And yes, they are different. According to Mitchell's institute's research, the euphoric sensation of oneness with the universe creates brainwaves similar to meditating monks. Mitchell's studies were so significant that NASA launched a special Space Shuttle mission in 1998 just to study the effects of space on the brain. The Neurolab mission studied brain cells of laboratory animals, and the astronaut crew too, as brain cells try to adapt to the freefall environment in low Earth orbit. Well, we can't all be astronauts, but now we can all access virtual reality experiences of what the astronauts saw in space. The internet has opened up our earthbound point of view to share the unity and oneness of the overview effect, and give us a small taste of the space euphoria astronauts get in space.